Welcome to today's class on satellite communication. Uh, Topics will be covered today is satellite up and down link, InterSatellite Link, then RF link budget, a study of noise figure, noise temperature, and antenna temperature. We'll discuss satellite antenna temperature for today's class. So up and down link. As we all know, satellite having some base station at the ground. So from base station to satellite, this link is called uplink, and from satellite to base station at the ground, this link is called downlink. This is basically a geostationary satellite having 36,000 kilometer height from Earth's surface. So you can see it from here. We have taken example of three basic satellite operating on C band, Ku band, and K band. Uplink frequency is a bit higher than downlink frequency. If it is a C band satellite, uplink frequency is near about 6 gigahertz. Downlink frequency is near about 4 gigahertz. If it is a Ku band satellite, uplink frequency is 14 gigahertz. Downlink frequency near about 12 gigahertz. For Ka band, it is 27.5 to 30.5 uplink, 17.7 to 21.7 downlink frequency. So why this uplink frequency is higher than downlink frequency? It is self-understandable because uplink frequency means from ground station to satellite. So this is on the ground having high power transmitter to transmit high frequency signal, because frequency have to cover the entire atmospheric distance to reach the satellite. So this is higher for higher frequency. And now this satellite is operating on a solar panel, so power handling capability is slightly less, so use lower frequency to transmit for downlink, and corresponding signal loss can be compensated by using very high sensitivity receiver at the receiving base station. If it is a mobile communication, the exactly opposite thing happens, because uplink frequency is lower. Sorry, uplink frequency is uplink frequency is lower than downlink frequency. It is also self-understandable because uplink means your cell phone to base station, your cell phone having very small battery and small microstrip patch antennas, and downlink frequency from base station to your cell phone, that means base station having high power. So the thing is like that. InterSatellite link is basically the link between two satellites. It can be on geostationary satellite to on low Earth orbit satellite, or even in between two geostationary satellite. This link is basically called InterSatellite link, and according to International Telecommunication Union recommendation, InterSatellite link within two geostationary satellite, or even on geostationary to geosynchronous satellite, having 4 specified allocated band. One is 22.55 to 23.55 gigahertz, 24.45 to 24.75 gigahertz, 32 to 33 gigahertz, 59.3 to 71.1 gigahertz, 0 gigahertz. Same link is also used for the link between on geostationary to another non-geostationary satellite. The same link can be used. For RF link budget, it is basically a phenomena how power, that means signal power, get deteriorates with the distance. This is basically the transmitting end. So let's consider this is at the ground station, ground transmitting station. So this is the initial transmitting power of the signal. Now this transmitted signal passes through the cables having numbers of connectors. There may be mismatch, so there will be some losses mentioned by this red color. Now this transmitting antenna having some power amplifier, so it is amplifying some power level up to this much. Now this signal transmitted through the antenna, this is in the ER medium, So this signal is passing through the atmosphere to reach the receiver. This is receiver. So as this is passing through the wireless medium, having some losses due to shadowing, fading, and multipath. So we are having this much amount of power losses. Now this is receiving antenna having some power amplifier as well. So this is amplifying the power again. Now this power is passing through the cables of the receiving stations. So having some losses. Now this is the level of the signal which ultimately get received. This is the power. And now we have each and every receiver have some specified level. This is sensitivity level. If you receive any signal lower than this level, then that will never be detected by this type of receiver. So this is my actual received signal power. This is the minimum received power. This margin is basically called link margin. This margin marked by this arrow is called link margin. If attenuation is more, if attenuation is more, then in any condition, if this received signal power is less than the sensitivity level, then that can never be detected. In that situation, you have to increase the transmitting power again to receive the signal properly here. Now, as I said, received power is basically transmitted power plus gain minus losses. PRX is the received power. This is the transmitted power. That means this is the power used during the actual transmission of the signal. This is the gain due to transmitting antenna. This is transmitted. This is transmitted antenna gain, GTX. GRX is the gain of the receiving antenna again. So we have these two gain portion, and we have losses as well. L of TX is basically the transmit feeder, connector, and associated losses. L of FS is basically free space path loss. That means path loss in the wireless medium due to shadowing, fading, multipath. LP is basically signal loss due to propagation. This is the propagation losses, and LRX is the again feeder, connector, and associated losses at the receiving end. So ultimately, adding the gain with the transmitted signal and subtracting the losses, will have received power. And this received power supposed to be more than the sensitivity level, this level of the receiver. Now we'll discuss a bit about noise. Um, Basically, noise means unwanted interference from nature. In case of satellite communication, it may be noise due to cosmic noise, galactic noise, and all other atmospheric noise. And as we know, noise power is basically KTB. K is the Boltzmann constant. Now noise figure is basically, as you know, input side signal to noise ratio divided by output side signal to noise ratio. And if we have cascaded amplifiers or cascaded device having the different noise figures and different gain, say F1 G1, F2 G2, F3 G3, then ultimately accumulated noise figure should be like this: F1 plus F2 minus 1 upon G1 plus F3 minus 1 upon G1 G2. Likewise, so we'll have a brief illustration here on my notes. So this is a register. This is noise. This is a noise equivalent temperature T. So noise power voltage level of noise is basically 4H F. B into R. B is the bandwidth, F is the center frequency, H is the Planck's constant, and R, you know, this resistance value. H is the Planck's constant, value is 6.626 into 10 to the power minus 34 2 second. K is called Boltzmann constant, 1.38 into 10 to the power minus 23 joule per Kelvin. So this, if we expand this exponential term, if exponential of HF upon KT, it look like this. So under the consideration that frequency is of 100 gigahertz and the temperature is 100 Kelvin. So HF is 6.6 into 10 to the power 23 and KT is 1.4 into 10 to the power minus 20 on. So HF is, can I say, HF is less than KT. So under this consideration, this exponential term will reduce like this. Exponential HF by KT is 1 plus HF by KT, and we are neglecting the higher order terms here, this higher order terms here. So HF by KT is basically so now Vn square, this noise voltage level will reduce like this for KT R into B. Now this noise voltage is passing through, let's consider some phenomena. This noise voltage is passing through the input resistor R. This is ideal band pass filter. This noise power appearing across the load resistor R again. So this noise power is basically I square into R, means Vn upon 2R square into R is nothing but KTB. As we all know, noise power is KTB. So noise figure is a signal to noise ratio of input side to the signal to noise ratio of the output side. So output signal is basically gain times of SI. This amplifier having gain G, so G times of SI. And output noise is basically G times of input noise, gain times of input noise is Ni, plus del N is the noise introduced by the device itself. So if we simplify this thing, we'll have value of del N as F minus 1, that's noise figure minus 1 into G into Ni. So this is the value of delta N, that means noise introduced by the device itself. So if we have this type of device cascaded, then we will have this is the input signal to noise signal, this is input noise, this device having gain G on, F1 is the noise figure. Here we will have output of the first device as well as input of the second device. For signal it is S2, for noise it is N2. This device having G2 gain, F2 is the noise figure. Ultimately we are having S3 signal output, N3 signal, noise output. So S2 is basically G1 times of S1, N2 is G1 into N1 plus del N. Del N is the noise introduced by this device. So G1 into N1 plus del N means, as we have earlier here, F on here, F1 minus 1 into G1 into N1. So ultimately we'll have F1 G1 into N1. Here S3 we are having, S3 means G2 times of S2. So, and if we put the value of S2 here, and as you know, S2 is equal to G1 into S1, so it is G1 into G2 into S1. For N3, it is G2 times of N2, gain times of this noise is multiplied by this gain, plus as like the earlier case, this is F2 minus 1 into G2 times of N on, this is not N2, why? Because this device, for this device N2 is the input noise, but this device and that device operates on the same environment. So environmental noise, this is basically the environmental part. So this is N1, not N2. N2 is the input noise of the device, but this device having input noise N1 because of atmosphere. This device also atmospheric effect of noise is also N1, not N2. So ultimately, simplifying this, we will have this much noise as N3. So if we mm, get ultimate noise figure of this combined device, um, where S1 is the input signal, S3 is the output signal, N1 is the input signal, N3 is the output noise. Sorry, N1 is the input noise, N3 is the output noise. So ultimately, simplifying this, we'll have F1, sorry, F is equal to, that means combined noise figure of the two device is F1 plus F2 minus 1 into G1. So ultimately, if we have n number of device, say F1 plus F2 minus 1 in, upon G1, F3 minus 1 into G1, G2 plus likewise it will go. Now equivalent noise temperature. This is not the physical temperature of the device. This is the noise temperature. Means some virtual concept, means this device is introducing some noise, and the equivalent temperature of that is called noise temperature. So let's consider N0 is the output noise of the device, S0 is the output signal, input signal is I, input noise is Ni. So as you know, N0 is basically G times of Ni. That means this input noise is multiplied by G plus del N is the noise introduced by this device. So G times of KTB, because Ni is the noise power, here it is KTB plus del N. So if I take KGB common, so I'll have T plus del N upon KB into G. So this is nothing but this del N upon KBG, where K is Boltzmann constant, B is the bandwidth, G is the gain of the device, is basically the equivalent noise temperature of the device. So KBG into T plus T. Now if we equate with the noise figure here, F is equal to input signal to noise ratio divided by output signal to noise ratio. So if we put the value of N naught here, so we'll have this, and after simplifying, we'll have this noise temperature is equal to F minus 1 into the temperature T. So if we have a cascaded system like this, then we'll have F1. For F1, it is 1 plus. So from here, F is equal to 1 plus T upon T. I have put this formula here. So F1 is 1 plus T1 plus upon T. F2 is 1 plus T2 upon T, means F2 minus 1 upon G. That is T2 upon T into G on. Similarly, F3 is equal to T3 divided by T into G on G2. So ultimately, as we know earlier, we have derived this formula. F1 is equal, F is equal to this, F1 plus F2 minus 1 upon G plus F3 minus 1 upon G on G2 likewise. So F is basically 1 plus T upon T. And if we put all the formulas, replace all the noise figures in terms of noise temperature, we'll have this. So ultimately, we'll have T, that means equivalent noise temperature, is equal to noise temperature of the first device plus noise temperature of the second device divided by gain of the first device plus T3 upon G and G2 likewise. Okay, get back to our slide again. So we are discussing the noise. So we have the noise figure. We have got the data of this data of noise figure. We have proved rather if we have a cascaded system, then equivalent of noise temperature is like this. Noise temperature is T times of noise figure minus 1. Similarly, noise figure is basically 1 plus T upon T. And if we have cascade number of device cascaded, so equivalent noise temperature T is basically T on plus T2. This is T on, T2, T3 likewise. So T on plus T2 upon G on T3 upon G on G2. Similarly, if we have a number of device, it will go like that. Fine. Now, antenna temperature. If we have a satellite antenna, now this is some satellite moving on the Earth. So certainly this ground station having some antennas, and angle of the antenna is on matter, because polarization of this antenna and the satellite direction will um, have some noise related issues. We have cosmic noise, galactic noise, and this all the atmosphere inside, in between this ground station to this satellite, it will also introduce some noise. And as you know, basically the antenna temperature, noise equivalent temperature of any antenna is given by 1 upon 4 pi. And this is double integration. Phi varies from 0 to 2 pi, and theta varies from 0 to pi. Uh, this is the temperature function of theta phi, um, times of gain of the device into sine theta d theta d phi. So each and every antenna having some pattern. This is the main lobe of the antenna. These are the side lobes. This is basically the angle theta. So based on this theta, noise of any antenna, satellite antenna, basically get varied. Look here, this is basically the satellite antenna. If we have this is our main lobe, and this is the angle theta. So based on the theta angle, background noise, and this is a curve, background noise versus frequency curve. As you can see, the theta, if theta is 0 degree, background noise with the frequency in gigahertz varies like this blue curve. If it is theta is equal to 20 degree, it varies like this. If theta is 90 degree, that means exactly this thing rotates, and exactly in 90 degrees uh, mountation with the satellite, uh, then we'll have um, more background noise as well. This is because of the interfering agent of the atmospheres, cosmic noise, galactic noise. So ultimately, the total noise of the system, it can be satellite end, or can be in the Earth station. This TS is the system noise, is basically noise of the inter-receiving system. Let's consider at the ground station, the center noise of the receiving system, noise temperature of the receiving system is basically equal to the antenna noise, that means noise temperature of the receiving antenna, and all other accumulated receiver system also introduce some noise. This is noise temperature of receiving system. So total, these two functions get added with the equivalent noise equivalent temperature of any receiving satellite antenna receiving system at the ground station. So I think we should stop here for today. We'll discuss atmospheric effect. That means ionospheric and all other atmospheric effect on satellite communication in next class. Thank you.